Okay, welcome to this user gathering or user meeting. Maria Grazia, what's the official name?
User meeting.
User meeting. That we decided to move, instead of having a 2-day event in Lugano.
Sorry,
it's a bit too loud.
We can try.
Okay. Like we had last year, to make it an informative event now, because we are planning to have a more of a scientific computing-oriented conference next spring. I think it's around May timeframe, to which we would then attach the user meeting, the traditional user meeting. But since we have a lot of news to tell you that cannot wait until next May, we decided to have this user meeting today here in Lucerne. So welcome, and thank you for coming, making the way. So I will, in the first half hour or so, 45 minutes, I will give you an update from CSCS, Piz Daint, so the new flagship system that we are building at CSCS, and I will also talk about this new platform for advanced scientific computing, PASC, that has been developed in the course of the last year. So those are the things I'm going to talk about, and then Maria Grazia, after I finish, will discuss the user program and a new call for proposal and a new process to handle proposals, very large proposals. And then I believe Sadaf will also talk about some of the programming environment on Piz Daint. So the news from CSCS, some of you may have heard it, for some of you may be the first time you hear it, that Dominic Ulmer, who was with CSCS for 8 years and was, since I came to CSCS 5 years ago, he was the general manager of the center. He decided to take a position with a company, Cray, and so he has a very interesting job there that allows him to grow and explore new things, and so he left CSCS. And this is, of course, not a small change to CSCS, because he played a very central role, and so we had to adapt our organization. So those who know me from the past, I'm somebody who's very slow at changing the organization, but if something like this happens, you have to react. And so what we did is, this may be more or less important for somebody who uses the machine, but just so you know, before we used to have a directorate that had Dominic and myself in it. We chose not to replace Dominic as a general manager, but rather change the organization, that now I am the director here. The staff that used to be attached to the directorate is now a unit that is led by Michele De Lorenzi, who is also my deputy. So when I'm gone, which happens quite a lot, he's my deputy at CSCS. But the rest of the organization, with scientific community engagement, future systems, technology integration, computing services, which are the units that you care about most. And of course, we have the infrastructure unit over here. Business services remains the same. So this is just from your point of view, what I just want to explain our organization. And if you have questions, you can ask me afterwards. Supposedly, the organization now continues to work, and you shouldn't have to worry too much about the details. Now, this obviously I forgot to do the build here. In terms of the roadmap, The place where we were last fall is we were in the new building with Monte Rosa being our main system, and this is still our main system, and we have this new system, Piz Daint, that was, I think, a year ago at the user meeting was just being announced. So we were in the process of installing the first cabinets. And since April, this system is now also part of the user program. And, but our main production system for the user program remains Monte Rosa. And Monte Rosa will stay around as a machine until, the plan is certainly until 2016. But what I want to talk about now is what is happening here, how we are building up this system. And then, of course, because we have a cycle of innovation, we also have to, at some point, then start worrying about whatever we do in 3 or 4 years from now, in 2016-17. So we're already, of course, in the budget planning for that phase as well. Sometimes this spring, we had to close down the HP2C platform, this high-performance, high-productivity computing platform that was funding a number of projects that were developing applications. And we have a successor to this platform, which is this platform for advanced scientific computing. And I will also say something about this, because this turns out to be then an integral part on how we move from this machine to the future, okay? Okay, so but now getting back to Piz Daint. So I will talk now about Piz Daint and then about PASC. So Piz Daint is really a Cray XC30, and CSCS, I believe, was the first site worldwide to install a large XC30. So something quickly about the history. This architecture was developed by Cray under the DARPA HPCS program, and it took like almost 10 years, the development of this thing. And then they had to build a demonstrator to DARPA. This is this Defense Advanced Research Project agency in the US that I'm sure most of you know, about a year ago in October. And we were then very quick, and the demonstrator was basically 2 cabinets, 2 or 4. I don't even remember that detail, but we were very quick in getting a batch. It was 4, because we then got 3 times 4 cabinets, initially operated as separate, and then we started to put them together into one network. And it was very important to have this build-up phase because this is a new, much more powerful network compared to Monte Rosa, and so it was very important that we do this in a systematic way. So that was the first phase, this new network interconnect that should have much better global bandwidth, shorter latencies, everything you dream of should come true here, within certain technical feasibility bounds, of course. Then the machine is also more efficient from an energy cooling perspective. I know most users don't care about it because they don't pay the power bill, but ETH pays the power bill, so they very much appreciate that we pay attention to this point as well. And this we had announced after a rigorous study that we did, CSCS together with Cray, in evaluating different node architectures. We came to a decision at the end of last year that we would upgrade the system or extend the system to hybrid nodes with CPUs, multi-core, so Sandy Bridge CPUs and GPUs. We were very carefully looking at all the options, particularly Xeon Phi, and we came to the conclusion that from an application performance point of view, the hybrid CPU, GPU is the most performant. Actually, the Xeon Phi in our application tests was not performing, and so, and our meaning really using applications from the user program here, So we basically decided we will continue to study Xeon Phi, but now is not the time to introduce this into a productive system, was our conclusion. And this was really done together with Cray. So now you can ask, if it's a CPU, GPU system, why are you not just building the Cray XK7, which we were also testing? And we now know, since we are building this new architecture, that actually Piz Daint will be significantly more efficient from a power use point of view compared to even Titan, okay? Which again is important for those who pay the electricity bill. Now, what does Daint or hybrid Daint look like? Well, you start to build a computer today with blades. And so a blade in Daint has 4 nodes, and every node has 2 sockets. Currently, these 2 sockets are populated with 2 Sandy Bridge processors. I will come back to these details of the nodes later. And then it has this Aries system on a chip, which is routers and network interface circuits together. So that's the networking part. And then there's a lot of cabling that comes out and in the back. And so then these blades, 16 of these blades are assembled together into a chassis, and so then all these network cables inside of this chassis, there's the first level of communication happening in the backplane of this chassis. And then there is a second level of this network, so these slides will go online and you will see them. It's basically, you have maybe hard to see from the back, but you have to imagine that every pair of sockets here is a node. And then here you have 4 nodes times 16. So you have 64 nodes, and they are interconnected in the backplane with an all-to-all. So these are 16 nodes, and you have an all-to-all interconnect in the backplane. And then 6 of these chassis, 3 in a cabinet and 6 in 2 cabinets, are then again interconnected. Every node, say node 0, is interconnected with an all-to-all. All the node zeros of one chassis have an all-to-all. All the node 1s have an all-to-all, and so on. And so this is like a 2-dimensional all-to-all, 2 dimensions of this topology that is called the dragonfly topology. And then you take one of these groups, and then each group is interconnected again with the other groups in an all-to-all fashion. Okay? So physically, there's a lot of cables in this machine, electrical cables and optical cables, and it turns out it works. So it's a highly non-trivial thing, but it works. It reduces the latencies because you have much smaller number of hops going from any place in the network to any other place compared to a torus topology. And it's also, the other nice thing is you can show this when you draw this all and you think about it, that you can scale the system, like you can double the size of the system by increasing, the cables that you pull in at this level. So the cost of the system goes linearly, and the global bandwidth also increases linearly with the system, which you don't have when you have a fat tree or so. There you reach, the limit of your biggest switch, and then you have to have a lot of money to buy an even bigger switch if you want to continue to scale the system. So this, so much to the network. And now we have a choice of nodes. So the original node that we had is 2 Xeon processors. So this schematic is basically the network on a blade, and the blade, I said, has 4 nodes. And they are assembled on 2 daughter cards that have 4 processors, so they are called quad processor daughter cards. And so every node two Xeon processors connected by PCIe bus, and on the same PCIe bus they connect to the NIC, and there are 4 NICs that are then connected to a router, and this is all on one chip of the Aries interconnect. Okay, and as I said, now we have a choice between this type of blade and this type of blade, which is the difference between these two is that we take one Xeon processor out and we put the Kepler GPU in there. And so what the configurations we have, the original one that we have running so far in Daint was 2 Intel SAMD bridge CPUs with 8 cores each, and 32, that's 32 gigabytes of memory. I have to correct this. It's good when I read the slides in the present. 32 gigabytes of memory, DDR3 RAM, and the hybrid node will have 1 Intel SAMD bridge, still 32 gigabytes of memory. So the RAM per node is not changing. It's just that instead of a SAMD bridge, we will have a Kepler GPU, and in addition to that, then 6 gigabytes of GDDR5 memory. And so the difference is, of course, the performance of this hybrid node goes up, provided you can use the GPU. Okay? And so now you can see these are the two options, and now we have a huge possibility. The performance goes up a factor 4 by doing this replacement, provided you know how to use the GPU. That's the caveat. Okay? And so the dilemma we have now is to put in this way. So I think we all agree we are interested in scientific productivity. Okay, so I think nobody questions this thing, that this is everybody's goal. Now, what do? Do we go with just continue to use current architectures and continue to just, maybe just continue to use Monte Rosa, but then you don't get the benefit of the new network, so just continue to use Daint with multi-core, okay? But already there, the question comes up, what is current? Is it single core, multi-core, distributed multi-core, mic, or GPU? So at some point, this dilemma, if you just say, let's stick with current architectures, you're just delaying the time when you will face the dilemma. On the other side, you can say, okay, let's bite the bullet and let's move forward with emerging technologies. And again, there the question is, or the risk you take is which emerging technology do I take? And you could become very unproductive because you're just dealing with new technologies and not with, and you cannot do any production anymore. And so you can trust me, we've spent a lot of time thinking about this and also discussing this with a number of users and collaborators and so on. And so we came essentially with a solution where I think with this hybrid Piz Daint, this new system that we are putting in place, you will have the possibility to explore both. Remain in the multi-core era and explore emerging hybrid technologies. And the way it works is in the following way. We will have one type of blade with hybrid nodes, but we have designed the system in such a way that you can use it in one of 3 ways. You can use it, one, as a distributed hybrid multi-core, so CPU, GPU architecture. In these cases, most of the time, the GPU is the accelerator, but there are codes that do this reverse acceleration, where most of the algorithm works on the GPU, and they ship some work back to the CPU. But most of the time, you would use the GPU as an accelerator. So that's one way the machine will work. The other way, the second way, is just as a distributed multi-core system. Then per core, you will have 32 per 8-core socket, 8-core or with hyperthreading 16 threads, you will have 32 gigabytes of standard RAM. So compared to Daint now, you will have like double the RAM. That's the advantage of this system. But we will make sure that the system, the new system, performs from a network point of view in the same way. So if you use today on Daint, I don't know, 500 or 1,000 CPU sockets on 2 per node, you will just use twice as many nodes in the future, and you get the same performance, at least the same performance. You will have more memory for the job. And then the third way, and this was a little bit of a stretch from a networking point of view, but also is something we are promoting, is that in some cases you want the jobs to run just on the GPUs. Now, very technically below down, you know that right now this is not possible because the GPU is not self-hosted. But from an algorithm point of view, you can consider it that way, that you spread the data over the GPUs, over the GDDR memories, for example, in a climate code, where you are memory bandwidth bound and where it is better to use the GPUs than the CPUs. You spread the data over the GPUs, and the communication works so that you can move data from one GPU on one node to another GPU on another node, and do this at scale. So this machine will be designed to basically satisfy these three models at scale and in an efficient way. When you go on Titan or Teddy, this third case will have problems with scalability, and we hope we will have fixed these. Okay, so this is the system as we are now building it up, and it will come into the user program next spring. In April, there will be an early user phase that will start earlier. Okay, but I want to see the machine first work and be accepted, so before we make any promises. But we have really a hard deadline. In April 2014, this machine will be online, and so Maria Grazia will talk about the user program that comes with this. Okay, but now I want to talk about, assume this is all going to work and we will be able to use the machine, okay, because I believe we are well prepared. Now we have to discuss how we move into the future, because you can view this machine as really an opportunity to remain productive and explore various new ways of using systems in the future, okay? But as we prepare the future, we really need to get into a systematic interaction between the center and the user communities. We've done this at a small scale by having a selected number of applications from climate, material science, geoscience. We had from physics and biology, so molecular dynamics. But at some point, we have, now is the time to scale this type of interaction beyond just a few selected applications as we prepare future upgrades of the design of future systems. And so what do we need in order to design systems? So this is now coming from our view. Well, what we need is scientific roadmaps and goals. What I don't want to have is a roadmap that says, I want to have, 10 petaflops in 4 years or 100 petaflops, and then you say, what exactly? Well, I mean, high-performance LIMPAC. That's the discussion we don't want to have, okay? We want to have a discussion around goals, but now you don't want to have 60 user projects and 60 goals. That's very difficult to handle. So that's why we've asked the user communities to come together in communities and define those, and do also some homework to define scientific roadmap that then translate. We work out the joint application and hardware roadmap. And so what we need is communities that we can partner with that commit to developing and supporting application codes and simulation systems. So I think I've said this over and over again, CSCS is not by itself going to ever take over responsibility of an application code. That is always going to remain the responsibility of developers of models and domain scientists out there. But we would like to partner with these communities and understand what the roadmap of the ambitions, the roadmaps of the communities are, and then we will do our share in developing the system, and we expect the communities will also take some responsibility in supporting the application codes. Not just the group for themselves, but for the entire community. And we have a number of examples here, and then out of this comes the ability to co-design a system, which means going from application software to libraries to node design and hardware design, where we are then partnering with vendors and developers of processors. And so the model that we have under this platform for advanced scientific computing is we have the supercomputer at CSCS that is today would interact directly with the users. It will still interact in the future with users, but it turns out now we have a number of communities that have been selected in a process over the last year by the university conference. So the primary ones are these 5: geophysics, climate, biology, material science, chemistry. So now let me quickly give a background before I get to the communities again on this platform for advanced scientific computing. It started off a few years ago as a grassroots effort at ETH, became a structuring project funded by the Swiss University Conference and is funded between 13 and 16, so this budget phase. And the participating institutions are universities, Lugano, which has the lead, but then Zurich, Basel, Geneva, Fribourg, ETH Zurich, EPFL. Those are the ones that were initially part, but it can be extended. Also, the communities can be extended, but you have to start with something at some point. You cannot just work in the abstract. And the goal is to develop domain science-driven, promote domain science-driven development of Swiss HPC, and a number of chairs, about 40 chairs across Swiss university are involved. And then we have, one of the focus of this is now use this community to co-design the system, systems of the future, and there is some funding in this project for this, and there is a call for proposal around these co-design projects. And again, the communities are climate and meteorology. Material science is the official name, I think, but it includes chemistry, because like CP2K is more of a chemistry code, and nanoscience, that's what most people are doing today, whether they are in physics or in chemistry. Anyway, then we have life science and biomedical is one network, solid earth dynamics, so geophysics, and then physics, which is really cosmology and astrophysics and plasma physics. So even, tokamak would fall under this. Okay, so now in terms of to get across what we mean by co-design, we are going to pick one of this community and quickly walk through a few ideas, and I'm happy to have discussions then after the session closes. So I'm picking climate and Cosmo. We could also pick this one. In fact, we could pick any one because we have examples of HB2C projects in any one of these. If I would pick material science, which is, I think, the biggest community here, I'm always, because I'm a condensed matter physicist myself, I'm accused, you talk about too simple things. So that's why, and then they always say, look at climate, so I'm taking climate now. Okay, so climate, we are looking at this Cosmo code that is heavily used at CSCS and is basically at ETH to study regional climate change scenarios and understand the evolution of climate over the alpine region. This is done at high resolution of 2 kilometer lateral grid, sometimes 1 kilometer, sometimes half a kilometer, running simulations over 10 years. And obviously this is then has to be embedded, getting the boundary condition from coarser models, because you cannot run a global model that has 1 kilometer resolution today, okay? But now you can say this community could have, or actually they do have in their roadmap, the ambition to go to global models, so instead of regional climate models, to global models at the same resolution, okay? So this, you can do the calculation, this is a million square kilometers, roughly, and the world is 500 million. Okay, so you can say if you want to go to global, you have to multiply this by 500. They are already doing it at this scale, so you can just go a factor 500, and then instead of 10 years, you would really like to do 100 years, so you would have to go a factor 5,000, make the machine bigger. Now, not 5,000 times bigger than Piz Daint or Monte Rosa, because they are using just a small fraction. But it's still a huge change, okay? And this type of a challenge that we want to be able to address together and see how do we design a system that can eventually do this, hopefully before the end of the decade. You can also say, well, we have another partner at CSCS, Meteo Suisse, that does very similar things, also runs a 2 kilometer model over a bit smaller domain, running a 24-hour forecast instead of 10 years, but they have to do this in 20 minutes. They don't do a graduate thesis on, PhD thesis on one run. They do this every day, many times a day. Okay, so it turns out computationally to be very comparable to the climate study. And here you could say, well, instead of running this once, we need to run it many times because of this butterfly effect and prognostic uncertainty, and you need to do ensemble calculations. So you can say, well, we would like to run this high-resolution forecast instead of once in 20 minutes, we run it 20 times. And that's actually a serious plan. And now you can say, well, make the machine 20 times bigger. But then again, the thing that we keep forgetting is that 20 times bigger machine uses 20 times more electricity. Or 5,000 times bigger machine uses 5,000 times more electricity. And that's where things become unrealistic. Unless we work together on designing new solutions. And these new solutions have to include hardware, I give it, but also investments in software. And so now I'm going to jump a little bit ahead and just say, in the context of this HB2C platform that we had, what if we were, with the codes we have worked together, do this factor 20? So instead of run it once, run it 20 times in the same time. As a base point, I take the current simulation running on Monte Rosa. So this is true certainly for the climate people in here who run on Monte Rosa. So that would be the current Cosmo code running a factor 1x. Okay. I can now move this code to Piz Daint as it is now. And then you will see it runs a factor 1.3x faster. And that's understandable because the Interlagos processor Sandy Bridge are roughly comparable. Sandy Bridge is a little bit better. They have very similar memory, I believe. Yeah, I think so. It's very similar memory. It's memory bandwidth bound. Sandy Bridge is a bit better, and that's why you see this factor 1.35. Now, this code has been under an HB2C project, and I have to emphasize it's not the only one. I could do the same story with CP2K because we've invested there as well. So it's a number of codes, but this is now just the example of this HB2C rewrite of the code running the same problem on the same machine. And then you get a factor 1.4 and about a factor 1.5 here. And so the new code in Daint is already a factor 2 in speed up. Now the new code runs also on GPUs, so now you can move it from Monte Rosa to Tödi or Piz Daint to this new hybrid machine, and then you will, it will jump, and this is on a node-to-node comparison, it will jump a factor 1.7 roughly. Okay, so the accumulated speed up is a factor 3.36. And this is, and it could be made faster if we do this, combine the second and the third together, because here the CPU is unused. This one is running just on the GPU, and if you do the domain decomposition differently, it would be a bit faster, but we haven't been looking, or they haven't been looking at this. So this is one way of looking at the new machine. But the other way of looking at it, and this is also what drove the design, is looking at kilowatt hours used in the simulation. So here per ensemble member, every member is a high resolution simulation. On Monte Rosa, this would be just short of 6 kilowatt hours. Now you move the old code over to Piz Daint. We had just a factor 1.35 in speed up, but we get a 1.75 in reducing the energy to solution. And this has to do with the cooling system. The packaging on Piz Daint is more efficient than the older packaging in Monte Rosa. So that's why we get more than just the speed up out. The new code is really more or less just the speed up that we see. If you go to the other slide, I think here was 1.4 and here around 1.5. So we see that. But then the really interesting thing is moving it over to the GPU really gives you a significant energy efficiency. And actually we see this even with things like dense linear algebra results that you run, you know, the trivial thing, LIMPAC, on a cabinet of XC30, and you get some whatever number of flops out. Okay, I don't know what the number is. And then you run LIMPAC on the hybrid system, and so the number of flop goes up quite dramatically, sustained flop, but you actually see the power of the cabinet coming down by, you know, some not negligible, says roughly, I don't know, 5–10%. So it's interesting that you can get more performance, but less power. So the energy to solution gain can be quite interesting. So, you know, right, if we want to do a 20 ensemble member, we need a factor 20, but we already get a factor almost 7 in improvement right now. And I think as we move forward in the design, in this co-design of systems and software and application software, I'm sure we can reach the point where we can reach some of these goals, like global 1 kilometer simulation over 100 years with this factor 1,000 compression in time, using a reasonable system, you know, a system like today that uses a few megawatts and not gigawatts of power. So that's the goal. Now, in the last minutes, I want to just quickly say what this implies from an application point of view. This is the Cosmo code, different parts of the Cosmo code, assimilation, dynamics, physics, and so on, broken up in percentage of number of lines. And this is the code broken up in percentage of runtime. And you see a large fraction of the runtime is used by the dynamical core, another large fraction by the physics, and then a large fraction of the code is actually using just almost nothing in the time. And so the HP2C project that led to this new code rewrote the code in the dynamics and using C++ with CUDA backends for GPU, and moved the physics code with OpenACC to make it GPU capable. And so this was this rewrite of the project of the code. Now what I want to quickly discuss is the structure of the code to show how I believe in the future co-design projects have to work. Yes?
What is OpenACC?
That's open, it's an OpenMP like standard of directives, set of directives, so very similar to OpenMP, but it works in the context of basically for the SIMD model of a GPU. Okay, so it's basically the idea is you can take, and I believe Sadaf will say more about this, you can take a normal, a code that you have written for a multi-core processor with OpenMP, and now you can replace some of the directives to make it run on the GPUs. That's one way of moving a code. It's sometimes the easier way, not always necessarily the best way, but it's one of the options. And you can see in this code we actually use both. We use CUDA in some places and OpenACC in other places. But this is the code, the simplified view of the code. It has a dynamics part and the physics part, other parts that I don't want to discuss here because we really worked on these two. It has a main, and then it is built on a system that uses MPI. Okay. Now you look at the new code after the rewrite. The physics is pretty much exactly the same code with just different directives. The original code didn't run with OpenMP, but now it's OpenMP, OpenACC, and the dynamics is the part that has changed, where the actual dynamics is now much smaller code that builds on top of a stencil library. The stencil libraries were just inside here before. That builds on top of a library that deals with boundary conditions, which was also just in here, and then on top of a communication layer, which is also just in here before, and then MPI, okay? And so now what we see here is by rewriting this code, making it faster and more portable, because the stencil library now has backends for x86, multi-core, and GPUs. What they get is a new structure where you have the application code, some sort of intermediate library, and then the basic tools that we have on every system like BLAS, MPI, and these things. So the claim is now we have this intermediate layer of domain-specific languages or libraries and tools, and it is this thing that now you can say can be portable across domains, and that we need to pay attention in the development. And viewing it now from the point of view of model development, I think it looks in the following way. Up to now, we have a model, we have equations. We discretize the equations in this particular case, formulate algorithms, write the code, compile the code, run it on a machine. Okay, and that's this thing, how at least most of us see this development. I see a lot of people nodding, so you must be familiar with this. Okay, and here up to now we had the separation of concern was basically at this line, we deal with everything here. I mean collectively on the application side. Some of you just run the application, but some actually write them. So they go down here, and then the computer scientists take over. They write the compilers, okay? And so we have a clear line, and that's what we say separation of concern between computer engineering and computer science, and then here domain science, which to a certain extent involves applied mathematics as well, okay? The problem we have is this one computer abstraction or architecture doesn't exist anymore, but we have this plethora of processors and distributed different networks, whatever, down here, okay? So really, we have now a situation where the choice of hardware influences the choice of algorithm and implementation, and we already know that up here things are more complicated, that we iterate through model, implementation, algorithm, and so on. But it turns out we have a much more complicated set of interaction, which some of you in the lunch break correctly recognize that you start to need teams between computer scientists, application scientists, mathematicians, but the question is, how do you form these teams? Well, one thing you know is this is not a good place to draw a line if you want to separate concerns. Okay, so we have to do away with this, recognize that scientists design models and algorithms, methods around that, and this is driven by domain sciences, and computer architects design machines and driven by other markets like game industry or cell phone industry or whatever is the main funding sources to design hardware, okay? So these are like our boundary conditions, and what we need to understand is how to take care of the things in between, and so that's why I'm saying we need to draw the lines, the separation of concerns in two different places. I think topologically from this graph it's natural to draw it here. This needs a little bit more complicated considerations, why to draw it down here as well. But now we have to organize basically the thing in the middle. And this is what I mean by co-design within PASC. So we will fund interdisciplinary teams or groups of projects that are developing these, what I call domain-specific library and tools developments. Some investment also even as low as going down into some compiler, open source compiler development. So this is the idea of what we mean by co-designing in PASC. But it does require that communities come together, and and we are driving this process based on some goals that we have to, in the end, deliver a simulation that does something we want to do, something that is beyond the horizon for any individual group, but in a joint effort, you can actually reach this, like this 1 kilometer climate simulation. We should try to reach that sooner. Or you can formulate similar ambitions on the life science side, with molecular dynamic simulations running short of milliseconds and doing statistical averaging or things on the material science side and so on. So that's, I hope to have gotten across the idea of this whole, what PASC is about and what the machine is about, and I will stay also a little bit after the meeting so we can certainly discuss more.